Okay, so thank you very much, David, and yeah, welcome everyone. I'm going to talk about exploring the hidden environment underneath glaciers using our instrument called Cryoegg. I thought I'd give you a very brief introduction to my background. I've not worked in glaciology for very long. My background is in engineering, and I work for a number of big companies in the private sector and in the public sector, developing electronics for consumer products and industrial systems at various times in the past. But I've also worked in the polar regions several times. I worked for the British Antarctic Survey as an engineer in the past. And so I joined Cardiff about just coming up 18 months ago to work on this project for Liz Bagshaw, who's senior lecturer in glaciology, trying to develop and understand this a new instrument that she had conceived of. And I've put this logo on the bottom right hand side, this rather cute logo with the penguin and the polar bear. This is the logo of Pride in Polar Research, which is a network for LGBTQ+ people in polar research, of which I'm a member. So I thought I would start by trying to recap some of the glaciology I've learned in the 18 months that I've worked in the field. So if there are any glaciologists watching, you can pick me up on the points of detail later. But this is a sort of simplified view of a glacier, as if I've taken a slice through it. And what we have on the left of the image here is snow, and we have snow that falls on the glacier, and it accumulates on the surface of the upper part of the glacier and gradually consolidates. The snow becomes sticks together, and under the weight of the snow and with freezing and thawing, it consolidates into a sort of foam-like material which we call firn, and then gradually that material then consolidates further into ice. And the key distinction here is that the firn has a texture rather like the inside of a crunchy bar, in that it has a kind of open, porous texture. You can see here that each of the bubbles is connected to another bubble, so the water will flow through it. Whereas once the ice starts to form, the bubbles all seal off like the inside of a Whisper bar. Yes, I had to eat both of these chocolate bars to obtain the pictures. So yes, I'm sure that was a worthwhile exercise this afternoon. But the difference is that the ice is impermeable to water, even though it has bubbles within it, because the bubbles aren't connected to each other. So our snow falls, and then in the summertime, we then have the sunshine on the glacier, and maybe even some rainfall on it. And the result is we have melt water on the surface. If it melts or falls on the snow and firn, it soaks through to the bottom, but it can't penetrate into the ice. If it falls directly on the ice, it stays on the ice surface for the most part. And so what we get is a stream that forms on the surface. And that stream then flows down until it finds a place where it can escape into the glacier, and we get these holes which are called moulins, after the French word for mill, because they're like the water channel that forms in a traditional water mill, and the water just disappears down inside the glacier. And at some point, and this is a gross oversimplification, the water finds its way to the bottom of the glacier, and we have a channel on the bottom of the glacier quite often where the water flows down towards the glacier terminus. So we've got the ice moving quite slowly and potentially the water moving rather faster underneath it. And then beneath the glacier, we've got the bottom of the ice and then the bedrock beneath. And in between, there's this material called till, which is sort of like ground up sand and gravel that the glacier is dragging along underneath. And the reason this is all interesting to us is because if the water flows down underneath the glacier at the beginning of the season in the alpine type glaciers, then there's nowhere really for the water to go to begin with, and so the water is pushed down under the glacier, and because it can't escape, it lifts up the whole glacier, jacks it up, and that then acts like a lubricant. It makes the glacier slide much more quickly, and you can see in the springtime, if you make measurements of how the glacier is moving, you can see that the glaciers accelerate, and they move more quickly. But partway through the year, because obviously the water is lifting the glacier and then under high pressure, it finds its way into all kinds of weaknesses in the ice, and it gradually erodes away the bottom of the ice, and it forms nice channels, which you will often see in older glaciers if you go and explore them, And these channels allow the water to run away much more efficiently. And so this transition between these two different regimes, the kind of early regime with the water at high pressure, which is called an inefficient system, and then the later regime where the water flows more efficiently, is called an efficient system. That's really interesting, because if we know how this affects the glacier's motion, then we can understand how quickly glaciers are going to move towards the terminus, and in the case of places like Greenland, move towards the sea and dump ice into the sea, raising the sea level. So in understanding how glaciers respond to climate change, this is a big unknown, because it's a very difficult area to study, because all the interesting stuff that happens is buried underneath the glacier where we can't see it. So just to give you some pictures from the field, this left-hand picture is from Western Greenland, from a glacier I visited last year called Cermak Kuyalek in Greenlandic, or Stor Glacier. And this is it's actually a video, so I'll play this, and you can see that we have this meltwater running along the surface, and it going down this enormous moulin, and the spray producing this rainbow from the resulting spray. And on the right is a picture of a much smaller one on a glacier in the Alps in Switzerland. And these moulins are a very hazardous environment, and so it's really important to it's really difficult to study them, because they're full of fast-flowing, high-pressure water. Obviously, going down there would be bad for your health, and it's pretty bad for the instruments. If we put instruments into moulins on cables, the cables get tangled up and broken and damaged. So it's a very difficult environment to study. What we can do instead, however, it says clicking the wrong button, is we can make a hole in the glacier, and we do that with something. You can do it mechanically, but actually the quickest way is to use a hot water drill. This is one run by Aberystwyth University, and what it is essentially is a giant pressure washer. So here we actually have 4 industrial pressure washers which heat water and pressurize it, and then it goes into this large rotating drum around the drill rig here, and the borehole is actually here behind this chap, who is Paul Christopherson, who was the chief scientist on the project. And out of the end of the hose, there's a kind of shower head that's spraying the water out into the and making a hole. So we can make a long straight hole through the glacier, and we can put instruments into it, and that's really helpful. But the glacier is moving. This particular glacier is quite fast moving, and so what we find is that you put the instrument in the hole on the end of a cable, and the borehole will refreeze on a glacier in Greenland. So the cable is then trapped in the ice, and because different layers in the ice move at different speeds, then the borehole deforms and then the cable breaks. So after a few weeks or months, depending on how fast the glacier moves, the cable breaks and you lose your data. So all of this kind of boils down to why we would like to use a wireless system to explore this environment instead. So this is a sort of very simple explanation of how this is intended to work. We have our hot water drill borehole. We have our cryoegg, which I'll just hold up here. It's a cylindrical, a spherical instrument, sorry. And we put it down the borehole, and it sends out, it makes measurements in the subglacial channel, and then it sends those measurements by radio up through the ice to a receiver on the surface. The receiver picks up our data and relays it by satellite. And then the idea is that instead of it just being stuck in the bottom of the borehole, that the round shape means it will escape from the bottom of the borehole and run away down the subglacial channel, pushed by the force of the water, and it will carry on transmitting the data to our receiver on the surface. And we may need another receiver downstream, but that's easily enough to arrange. So that's the plan. And I was given this brief back in February 2019. Could I design and make this? So I had a good go, and actually on the workbench behind me, I put together this prototype, which has got 3 sensors. This with the sort of red sleeving on it is a pressure sensor. Then at the bottom left, the green board in the bottom left has a temperature sensor and an electrical conductivity sensor, and that sensor tells us whether the water is fresh or stale, if you like. Pure, very freshly melted glacier meltwater is very, very pure. It doesn't conduct electricity very well, but the water is a great solvent, and it tries to dissolve anything it can get its hands on. And so any kind of minerals that it comes in contact with, such as in the till on the bottom of the glacier, will dissolve in the water and increase its conductivity. So by looking at the electrical conductivity reading, we can tell, is it sitting in freshly melted water, or is it sitting in water that's actually been hanging around on the bottom of the glacier for a long time? In the middle, this white circuit board has a processor on it, which is basically managing the whole system. And then at the top is a radio transmitter, which sends the signal up to the surface. And I was very pleased to discover this. This is actually a system called WISE. It comes from the smart metering world. It's not used in the UK, but it is used in France and Italy and some other places. So this particular technology was designed for reading water meters in France, but it works on a very suitable frequency, a VHF frequency 169 megahertz, which works well for penetrating through the ice. And so it was very pleasing to be able to incorporate this ready-made technology into our instrument. Saved me a lot of time and stress. So having gone from a prototype laid out on a board like that, I then took all the relevant components, designed them onto 3 circuit boards. So this is the resulting electronics. So at the bottom here we have the sensor board in the middle with the processor, a battery there, and then the radio on the top. So finally that then is then wrapped in some plastic casework, and if I hold up the one I have to the camera, you can see that we have this nearly spherical casework with the top that lifts off, and there's a rubber sealing ring that helps to keep the pressurized water out. And so I designed and arranged to have made all these different components in about 5 months last year in order to go into the field at quite short notice. Obviously, the other end of the radio link, we need a receiver. So we have this large antenna, and the reason it's quite large is because that helps us to pick up a weak signal. And here it is in Greenland, in the East Greenland ice core drill trench. And we have this green plastic thing here, which is actually a climbing frame toy called Quadro. It's made in Germany, which turned out to be very convenient because I wanted something non-metallic so as not to disturb the radio signal, but also quite convenient and easy to use. And the Quadro company were quite amused when I wrote to them and said I wanted to use it for science and let me have it for nothing. So that was very kind of them. But the data, the signal from the antenna comes down this black cable into the receiver box, which you can see here on the workbench, and then onto the laptop, and we get our data in real time. So it's really helpful when you're working in the field to be able to see what you're doing in real time. So this, from an engineering perspective, created quite a lot of difficult challenges. The main one was the radio link performance, making sure that we actually would get the signal through the several kilometers of ice, which a lot of people were a bit dubious about. A big thing I was concerned about was power consumption. One of the challenges with any kind of wireless instrument is that you have to run on a battery, whereas with a wired instrument you can send power down the cable. So we wanted to make the power consumption as low as possible. And so the way it's designed is it works a bit like an alarm clock. The processor has a clock in it and a quartz crystal like you would have in your wristwatch or in a wall clock. And this clock circuit within the processor is used as an alarm, so that when it's time to make a measurement, it wakes up, turns on all the rest of the instrument, turns on the sensors, makes the measurements, encodes them into the right format, turns on the radio transmitter, sends the signal to the surface, then switches everything off again and sets the alarm. And whilst it's in sleep mode, it uses almost no power at all, because all it's running is just the quartz crystal to keep the clock running. The other thing that was a big challenge, and is still a challenge because this is my first project involving some mechanical engineering, my background is in electronics, was making the thing sufficiently robust. And Liz had done some previous work with another engineer, Ben Lishman, on designing the casework, so that we had a bit of a head start, but we've had some issues with the instrument leaking, and so that's one of the things I want to address in the next round of design. So how did we get on? We went into the field, and in 2019 we had 2 successful field deployments. The one here shown on the left, this is the East Greenland Ice Core Project borehole. So they are drilling a a long ice core, about, ultimately, if it goes all the way down, it will be 2.5 kilometers long in northeast Greenland into a very fast moving part of the ice stream, which is all very interesting from an ice coring perspective. From our point of view, it gives us a long borehole into a fast moving glacier, which ultimately we would like to deploy Cryoegg from this borehole maybe next year. But we had a test last year because they'd finished drilling at the end of the season. They let us put the instrument in the borehole, and we lowered it down on the end of the winch. You can just see it going into the borehole there. And we got data from about 1.3 kilometers down. And I had hoped to get data all the way to the bottom, but that didn't come to pass. And the instrument, it turned out when we got it back that the instrument had leaked. But it did pretty well down to 1.3 kilometers, and that's the first time that anyone's done that on this kind of frequency and using this kind of technology to that level of depth. So that was exciting, but there's more work to do. And then a month or so later, we were in Switzerland on the Rhone Glacier, and here you can see the sort of slightly less glamorous side of glaciology that has been kneeling on a glacier, staring at a laptop in the bright light, and picking up signals from Cryoegg which was in a small moulin, and we were able to see the water level change in the moulin in real time, and that was all very promising, and we hope to do some more experiments there in the future. But not everything went according to plan, as it rarely does in field science. We had one attempt in Greenland last year, which failed because the instrument wouldn't go down the borehole. The borehole wasn't big enough. It's often quite difficult with a hot water drill to work out how big you've made it. And we had a trip back to the Rhone Glacier at the last minute this year when coronavirus restrictions were briefly lifted. We went dashing off to Switzerland to try and do some experiments, but we had big issues with Cryoegg leaking. It turns out that the assembly process, I basically got lucky last year with pouring the adhesive sealant into the instrument and got a good seal this year. I did it slightly differently and it didn't work. So there's definitely more work to be done. So plans for this coming year. I want to improve the mechanical design and eliminate the leaks. And we're going to try and go to the National Oceanography Centre in Southampton, where they've got a pressure tank that they use for testing little robot submarines, and we hope we can test it there in their tank, and make the pressure sensor, which sticks out through the outside of the case at the moment, make that more robust so that it's not damaged if the instrument's put into it hits against the side of the borehole or in a moulin. Going to improve the radio performance. The antenna that's inside Cryoegg at the moment is not as good as it might be, and I think we can improve that. And then we're going to change to a higher capacity battery, one made by a company called Tadiran, which will allow us to make more measurements more frequently for the same amount of total deployment life, so we get more data. So that would be really helpful. There's a data logger and satellite terminal that sits on the end of the receiver, and that needs some improvements as well. So that's the plan for this year. And then hopefully, I was just at a seminar yesterday where they were talking about the plans for the East Greenland Ice Core. They're hoping to run their field season again this summer in June, July. It depends a little bit on what support they can get from the Americans, but we would hope to be there in August. And if they've drilled all the way to the bottom of the borehole, to the bottom of the glacier at 2.5 kilometers down, then it would be great to do a test there and maybe even a deployment. But certainly, even if they don't reach the bottom, it would be really helpful for us to go again and do a test. So that's the plan in the shorter term. In the longer term, and these are more kind of aspirations rather than detailed plans, we'd like to use some new types of sensors. So Liz, her particular interest is in looking for microbial life in these water channels underneath the glacier, because pretty much wherever there's water, there's life. And nobody really knows very much about this at this stage. So we're going to try and find some other types of sensors, and we can use the basic Cryoegg technology, the radio link, the processor, the battery, and all the rest of it as a platform, and then change to put different types of sensors on for different experiments. So we'd like to measure pH and dissolved oxygen, and there are various other sort of more exotic biosensors being developed at other universities that might help us look for microbial life in these environments. I'd also like to do some new variants of the instrument. Some of these I've started a bit of work on already. A lot of glaciologists like the idea of Cryoegg, but actually they work primarily by making boreholes in the glacier. And if you make a borehole with a hot water drill, then the size of the borehole is basically determined by how much fuel you use. So if you use a bigger borehole, you use a lot more fuel. So they looked at the spherical cryoegg and said, well, that's all well and good, but it needs a really big borehole. If we can pack the same electronics into a long, thin tube, then we could use that for borehole studies. So I'm doing a version of that. Because it's shaped like a sausage and because I work with some German-speaking colleagues, it's become known as cryoverse. And then my colleagues who work in snow science and river hydrology also were interested in the technology, and they don't need the high pressure casing that we need for glaciology. So we're going to do a lower cost version in a lighter weight case, and that's become known as cryobeam. So yeah, quite a lot of interesting prospects for this technology. I'd like to give some acknowledgements to various co-authors and supporters and the commercial companies that have been involved as well. So yeah, thank you very much. I'll take a few questions. I'm just going to put up a couple of links on here which I can put in the chat afterwards with links to some other material. There's another video with a more technical seminar and a paper preprint you can reread if you'd like more technical details. But thank you very much.
Thanks a lot, Mike, for that very interesting talk. It's really good to know a little bit more about technical aspects associated with all that exciting research. I'm just realizing actually that my background is very thematically oriented today. Actually, these are the Swiss Alps, not far away from the Rhone Glaciers, so kind of funny. I didn't plan to do this, it just happened this way. So there are already quite a few questions, 5 questions, I think, which I'm really happy to read for you. The first one is, does the glacier ice density change at depths, and if it does that affect the depth at which water breaks out horizontally to the sea, or is that more dependent on running on top of the rock surface? And there is a slightly associated question, which is, does pressure from above heat the lower ice to form water?
Okay, so this is getting a little bit beyond my level of glaciology, I must admit. Yes, I believe the ice density does change with depth. But I would refer you to one of my colleagues. I must say about the details of how that actually works.
Yeah, fair enough. I don't know much about actually glaciology, but the question about whether the pressure is going to change the phase of the water, so from ice to water, is real actually, because you know water when it freezes is going to turn to ice, which has a higher density, a higher volume. Sorry, higher volume, not a higher density. Yeah. And so therefore, if you take ice and you just put a lot of pressure on it, it wants basically to reduce volume. And the way to do this is to turn it back to water. So I think if I'm well informed, there are some really interesting example of this process in Antarctica, where the ice cap is really, really thick. So the pressure below the ice cap is so big that actually you can have liquid water. That makes actually subglacial lakes, which are really strange. And yeah, there's been a few studies on these, like, you know, what sort of light would you have in these sort of features? Another question, which is more related to what Mike, I think, does. So what buoyancy level do you set? Does it, so your cryoeggs, do they scrape along the bottom or the roof of the pipes or the conduits in which they go?
So it's definitely negatively buoyant. It's definitely set to be reasonably heavy. Liz did some work some years ago, originally working with neutrally buoyant devices, which were intended to float in the stream and be drawn along as tracers so that they would be found again at the end of the glacier. Yeah, it turns out that actually if you have a waterfall, you get a kind of eddy that forms at the bottom of the waterfall. If you have something that's too buoyant, it just gets stuck there forever. So actually having something that's a bit heavier and slightly denser than water means that it will tend to get drawn away from that environment. So yes, Cryoegg is reasonably heavy. It's certainly denser than water. It sinks pretty well.
Great, thanks. So batteries aren't well known for their performance at low temperatures. So does the Cryoegg case insulate sufficiently to contain the heat from the electronics, or is it not actually a problem?
Okay, so yeah, the eternal battery question. So yeah, the battery, you're right that batteries don't perform well at low temperatures. There are actually 2 challenges there. One is that the overall capacity of the battery is reduced by the cold. So we solve that problem by basically having a bigger battery than we need so that we can lose a lot of capacity in the cold. And the other issue is that at low temperatures with a lot of batteries, it reduces the amount of peak current that the battery can supply. And the radio transmitter, when it transmits for a short period of time, needs a lot of peak current. So one of the reasons we're redesigning to use the battery from Tadiran in the next iteration is that that battery stores a lot more energy, has better cold performance, and we actually use it in parallel with a supercapacitor, which provides the burst of peak current for the transmission. So that's intended to address that. But yeah, there's no real issue with using batteries in the cold. You have to use a much larger battery than you expect, or than you would do at room temperature. But yeah, it's perfectly possible to make batteries work at low temperatures.
Cool. Have you considered filling the cryoegg with a non-conductive fluid, thus making it pressure resistant and less likely to fail?
Yeah, that's a good point. And various people do fill things with potting and so on. And in fact, electronics can be filled with rubber potting. And actually, the challenge there is filling it completely and making sure that you get all the air and gas out of it. And people use kind of sophisticated degassing techniques. I'm hoping not to need to do that because it makes the instrument very tricky to work with, not least in terms of switching it on and off and things like that. But yeah, if we had to, then we'd try to. Then we could, but I'd rather not, because it causes lots of other difficulties.
Yeah, great, thanks. I think there are a couple of questions that are closely related, which I'm going to read in sequence. So in a successful deployment, do you attempt to retrieve the cryoegg? Does it ever appear out from underneath the other end of the glacier, or is it intended to be lost? And how do you get the cryoegg back after releasing it into the glacier?
Yeah, so we're not expecting to get it back. It's a one-way item, and they're not terribly expensive in the scheme of glaciology compared with the cost of the helicopter out to Greenland. Then the cryoegg costs about £1,000, so it's relatively cheap, and we can afford to deploy them. Obviously, there is a slight issue that it is making a mess, but yeah, we don't expect to get them back. The first one I deployed, I did write my name and address in, just in case somebody dredges it up on the bottom of the fjord in the future. But realistically, it's going to be buried in the bottom of the ice for centuries.
To be discovered by future geologists or glaciologists.
Maybe, yes.
Like, what is that very old piece of equipment in there?
Yes, yes.
And the last question that is still unanswered is, someone who's not really sure about why actually you don't insert the cryoegg at the moulin themselves.
Okay, yeah. So we're hoping to do a bit of both. So the advantage of borehole deployment is that if you drill the borehole and the borehole connects to a subglacial channel, and you can tell that because when you drill the hole, the borehole's completely full of water as you're filling it from the hot water hose. As soon as it connects to the subglacial channel, the borehole level drops. So you can see that you made a direct connection. So that makes a very easy deployment. The cryoegg goes straight down and out the bottom, hopefully. The challenge with a moulin, particularly a natural one, is that it has a kind of convoluted internal structure and lots of internal waterfalls with their own plunge pools. So if you put a cryoegg in a moulin, and we are doing this, but it's not, but it presents us with a sort of different kind of study, because the cryoegg will take some time to sort of percolate through this series of plunge pools and waterfalls and make its way all the way to the bottom. So yeah, we will do some deployments in moulins, but but we're also planning to deploy from boreholes.
Great. So yeah, I think that was oh, there's another question yeah, that is coming through here. So yeah, an interesting one actually. What is the operating life of the cryoegg?
So at the moment, in the current design, it's about 2 years. We think the battery life calculations are based around it making a measurement every 2 hours for about 2 years. With the new batteries in the redesign, I may be able to do a bit better than that. So ideally, I'd like hourly data for 2 to 3 years. I think we should be able to achieve that.
Yeah, great. So I think that was the last question. You recommended a few links, I think, for further reading if people are interested in reading.
Yeah,
perhaps
let me just stick those through.
Yeah, bring them back on the screen as I just said. a few last words. So yes, so that's, I think, the end for today's event. So have a look at the links before you leave that geo talk. Next week, I'm going to be your presenter. I'm going to talk about something quite different. We're going to go to the tropical environment. More particularly, we're going to go to Panama, and I'm going to try to show you why the formation of Panama has had a very large range of global effects, including actually our, in a way, our lifestyle in the UK. So these are the two links that you are encouraged to look at. Remember, this presentation has been recorded, and at some point, which I hope is going to be relatively soon, the presentation is going to appear on our YouTube channel as well. So thanks very much, Mike, for giving that very interesting presentation today. Thank you all for attending, and I'm looking forward to seeing you again next week. Goodbye.